Okay, so our next speaker is Dhiren Pradhan here from the Carnegie Institution for Science, and he'll tell us a little bit about some interesting composite multiferroic materials.
Good morning, everybody. Thank you. So today I am going to talk about room temperature multiferrogym in PFN nickel zinc iron composite thin films, and I am working with Professor Ron Cohen, and this work is collaborated with Oak Ridge National Laboratory and Professor Ram Katiyar, Salini Kumari from West Virginia University, and Professor James Scott. So my outlines are why composite structure are really needed, and the mechanism of magnetoelectric coupling in multiferric composites, then my motivation, then my sample preparation, then results and discussion, then I will conclude my talk. So in 1894, Pierre Curie predicted that materials should exist which can be polarized by a magnetic field and magnetized by an electric field. Perhaps this leads to the discovery of multiferric material. Multiferric materials are those materials which have at least two primary ferroic order exist in same phase. The primary ferroics are ferroelectric, ferromagnetic, ferroelastic, and ferrotoroidic. So due to the mutual frequent incompatibility between electric and magnetic order, there are very few multiferroic exists in nature, and among them these are some common examples of multiferric materials like bismuth iron oxide, bismuth manganese oxide, lead iron niobium oxide, yttrium manganate, and magnetite. Among all, only bismuth ferrite is known as the room temperature multiferric materials, but it cannot still it is not applicable for practical device due to its high leakage current and high dielectric loss. And the other multiferric material has either the ferroelectric or ferromagnetic transition below room temperature. So due to this large independency between the ferroelectric transition temperature and ferromagnetic transition temperature, the magnetoelectric coupling is very small. So in order to achieve strong magnetoelectric coupling above room temperature, composite structures are needed. So why multiferric composite structures? The advantages are we can get combined high values of electric and magnetic polarization at room temperature, and we'll get higher effective magnetoelectric coupling coefficients, and we'll get wide range of operational temperature for multifunctional application. We can get both the ferroelectric and ferromagnetic transition above room temperatures. So during the synthesis of composites, as it is ferromagnetic and ferroelectric phase, we have to taken care a lot of things like chemical. There should not be any chemical reaction between the ferroelectric and ferromagnetic phases, and the electrical resistivity of ferromagnetic phases should be very high to minimize the leakage currents, dielectric loss, in order to withstand the high electric field. And during the synthesis, mechanical defects such as pores of the ferromagnetic and ferroelectric phase should be taken care, and we should grow like atomically perfect epitaxial growth of either multi-layer or composite single layer thin films for perfect mechanical strain transmissions. So there are like three types of composite structure. Structure one is 0,3 particular nanocomposite means in a ferroelectric matrix there should be ferromagnetic particle, and another is multi-layer of alternative ferroelectric and ferromagnetic material, and another is 1,3 vertical heterostructure with one phase nanopillar and embedded with a matrix of other phase. Magnetoelectric coupling is normally indirect coupling, and it is via strain. Here, there are two types of coupling. One is direct magnetoelectric coupling, and another is converse magnetoelectric coupling. The direct means by applying a magnetic field, we can change the electrical order parameters. Here, when we apply magnetic field, due to magnetostrictive deformation occurs in magnetic phase, and it transfers to the ferroelectric phase. Then, due to the piezoelectric effect, we can see the changes in order parameter. And in converse magnetoelectric effect, by the application of electric field, we can see the changes in magnetic order parameters. So, we have synthesized PFN and nickel zinc iron oxide composite thin films in order to achieve room temperature multiferrogym with strong magnetoelectric coupling. Here, PFN means PFN is one of the multiferric material, and it has monoclinic structure. It has high piezoelectric coefficient, low loss tangent, and its ferrority TC is around 379 to 385 Kelvin, and it has excellent ferroelectric, magnetic, and ferroelastic properties. And nickel zinc, we have chosen the magnetic material as nickel zinc iron oxide, as it is a ferrimagnetic material, and it has cubic spinel structure at room temperature, and Tn nil temperature is 600 K, so that we can get the composite structure have a magnetic tension above room temperature, and it has low coercivity, high resistivity to withstand high electric field, and high magnetostriction coefficient. It has good thermal, chemical, and structural stability, and this composition, nickel 65 and zinc 35 composition possesses the highest saturation magnetization in the entire nickel zinc series. So this is our means 1 minus X PFN, and means we have synthesized 10%, 20%, 30%, which can be abbreviated as PFN, PN1, PN2, and PN3 throughout the talk. So we have synthesized the thin film, single layer thin films, because previously we have synthesized some multi-layer, but due to substrate clumping, we could not get such high magnetoelectric couplings. So that's why we plan to grow some single layer thin films with a PFN and ZFO composite. And we have started this synthesis with a single target of PFN and nickel zinc iron oxide, and these are the optimized parameter. We have grown at 20 milliliter of oxygen pressure. The substrate temperature was 600 degrees Celsius, and we have annealed the sample around 700 degrees Celsius for 30 minutes at 300 torr of oxygen in order to avoid oxygen vacancy. And the laser frequency was 5 Hz, and the laser frequency was 5 Hz, and the fluence was 1.5 joule per centimeter square. And the bottom electrode was lanthanum nickelate, and for the electrical characterization, we have made the top electrode as platinum. So these are the X-ray diffraction pattern of pure PFN. This is a pure NGFO, and these are the composite structure. Here, in PFN and NZFO, we only observe the L00 peaks, means for PFN we only observe 100, 200, 300 peaks, and in NGFO we only observe 400 peaks. So, and in composite case, we also only observe the L00 peaks. Here, in the composites, we observe both phases of PFN. The H peaks corresponds to PFN, and the end peak corresponds to the NGFO. So we observe both PFN and NZFO peaks, and so means we can tell that the formation of composite structure. And here we also observe with the increase of magnetic content, the peaks of the intensity of peak of NGFO goes on increasing, and we did not find any intermediate or secondary phases and peaks from lead deficient paracolor phases. So from the X-ray diffraction, we can tell that the quality of the films are good. So in order to confirm in our thin films whether all elements are present or not, we have carried out the XPS studies. So here all lead, iron, niobium, and oxygen, and nickel, zinc peaks are present. So observation of all photoelectron characteristics of lead, iron, niobium, nickel, zinc, and oxygen confirmed the presence of all individual elements. And for the representative of all the films, we have carried out, I have presented only this. So this is the dielectric property in order to prove the ferroelectric phase transition of all the composite structures. So this is the dielectric spectra of PFN, PN1, PN2, and PN3. Here means as the magnetic content goes on increasing, the ferroelectric phase transition also, ferroelectric phase transition temperature, Tc, goes on increasing. And all this composition shows like relaxer behavior. Here with increase of magnetic content, you can see for PFN it is around 400, and PN1 it is around 430, and for PN2 it is 440, and for PN3 the ferroelectric phase transition is around 460 Kelvin. So in order to confirm the ferroelectric nature of all the thin films, we have studied some band excitation PFM measurement. So here we have polled the sample with positive and above positive and negative 5 volt. So we can see the phase contrast in positive and negative area. So from this we can tell that all the composite thin films exhibit ferroelectric character. But this behavior can also be seen in some non-ferroelectric material. So due to electrostatic effect. So in order to avoid, means in order to rule out that our material means this behavior is not due to electrostatic effect, we have carried out some other studies. So here this is the this all these are data of PFN, pure PFN1. So here we observed we have observed PFN. This is amplitude versus voltage. We have means we got butterfly amplitude behavior in PFN thin films, and with a phase flipping of 180 degrees Celsius. 180. And we have carried out also the piezo response. Here is the means out of field measurements, means of field measurement, and this is the in field measurement. And we have done also in field minus out of field measurement. If it is linear, then there is no periodicity. So it is highly nonlinear. It can be concluded that it is periodic. And we have subtract the linearity part also, and here we got the nonlinearity means. Now we can safely say that our means all the films are ferroelectric in nature. So we have carried out some temperature dependent piezo response measurement in order to corroborate the bulk ferroelectric phase transition, and this is the TP-induced ferroelectric phase transition. So as the temperature increases, the piezo response goes on decreases, and above 125 degrees Celsius, there is means the piezo response vanishes. Hence, in both the case, means out of field and in field, and this is the room temperature in field minus out of field. It is nonlinear, and in field minus out of field measurement, it is highly linear, means there is no periodicity above the phase transition temperature. So here are the ferroelectric means bulk this means the cross is the surface phase transition, and this is the bulk ferroelectric phase transition. Here means except PN2 means all the bulk and surface phase transition are approximately same. Then we have studied some magnetic properties of composite thin film. Before studying of composite thin film, we have studied the magnetic properties of nickel zinc iron oxide thin films. Here, this is the low temperature MH loop from 20 Kelvin to 395 Kelvin, and this is the empty core of low temperature. Here, means we observe a large bifurcation, which indicates that it is like slightly disordered type ferromagnetic system. And here, and as the temperature increases, the magnetization goes on decreases. And here, in high temperature magnetization versus temperature curve, we found the magnetic transition, and the magnetic transition is the ferromagnetic to paramagnetic transition is probed around 700 Kelvin. That's why we have included this nickel zinc iron oxide as a magnetic candidate in our composite structure. So these are the magnetic properties of composite thin films. Here you can see the PN1, PN2, and PN3 thin films. It has also some very less coercivity, and it has less remnant magnetization. And here also we observed that as we increase the magnetic content, and these are the field-cooled curve taken at 1000 Oersted. As we increase the magnetic content, the magnetic transition goes on increasing. And in all the PN1 and PN2 case, the magnetic phase transition is observed around the ferrotic phase transition temperature, plus minus 10 or 20 degrees Celsius. So, and in this is the PN3 one, but we are getting around 550 Kelvin. Here, all the composites of typical ferromagnetic-like hysteresis behavior above room temperature with high saturation magnetization, low coercive field, and low remnant magnetization. And we are also performing some fast principle calculation in order to understand the effect of magnetic content on origin and nature of phase transition, and the ferroelectric magnetic and ferroelectric and magnetic properties, and the nature of magnetic coupling, whether it is like PM square, P square, M square, P square, M, of all the composite thin films. So, means we have, in conclusion, we have synthesized high quality of PFN and ZFO thin films, and the presence of both PFN and ZFO phases with 0-0 pseudocubic reflection confirms the formation of the composite with highly oriented in nature. The ferroelectric nature of their thin films are confirmed by band excitation PFM. The ferroelectric magnetic transition TC are observed above room temperature, and both the TC increase with increase of magnetic content. All the composites show ferromagnetic-like hysteretic behavior above room temperature with high saturation magnetization, and high IME coupling is expected for all the composite as the ferroelectric and ferromagnetic TC are very close to each other. And we are acknowledging Carnegie Science, Oak National Laboratory, Office of Naval Research, and ERC grant, and computational support from HPCM. Thank you very much.
All right, any questions?
I understand that you didn't do any electric or magnetic field dependencies of your zone.
Yes, this is our next step. This is our next step to study some magnetic coupling.
Because at present you cannot say anything about a cross-coupling.
No. It is reported that if your ferroelectric transition temperature and magnetic transition temperature are close, then it means magnetodielectric coupling is there. But it is the indirect evidence. We are planning to study magnetodielectric coupling very soon.
It should be proven, of course.
Yes.
Other questions? I'll ask one real quick. In the PFM data, what was the different contrast for? There was like some splotchy yellow things. These are is there a phase separation? Like what am I looking at?
These are some, I have mapped the phase between what is the phase. I did not delete those things. So I mapped those areas so that to know whether the phase are really opposite to each other or not.
Other questions? All right, let's thank our speaker one more time.